signify the first moment of area about the z-axis. Okay. Now, I'm going to change it slightly. Now, what will happen now if the shear force, right? If the shear force is applied parallel to the x-axis, sorry, to the z-axis. Okay. So why I'm doing this, because at the end of the day, we are going to analyze what? We are going to analyze structure that is under 3D loading. I repeat again, we are going to analyze structure that are 3D loaded. So I'm going to now look at now if, okay, so we still have the same cross-sectional area. So I'm going to sketch out the same area now. Okay, so this is the area. So what we are going to change now, right? What we're going to change now is this, right? So that is, and then I'm going to draw out transformation. So the transformation is still the same. Okay, nothing changed. So this is your y, and this is your z. So now if we have a force now, our shear force is acting in this direction now. So this is our direction of shear force. Oh, I need to use a thicker one. So now our shear force is in this direction now. Right? So this is our V in the Z direction, right? There's our V in the what? In the Z direction. I want to put a Z down here. Okay, so this is our V in our Z direction now. Okay, so the area to analyze now, right? So the area to analyze now is what? Is now going to be what? Q what? QY. Okay, so the area of concern is now in this area now. Okay, so this is the area of interest now. Okay, so this will be equal to A Z bar. So Z bar is in this direction, so this is known as your what? This is your Z bar. Okay, so again, this is the first moment of area about the y-axis. Okay, right? So that is first moment of area. Then another thing to take note, right? Another thing to take note, if we look at the formula, okay, if we look at a formula, especially when we have a formula with a what? With a thickness in consideration. Okay, so now for this case, what is the thickness? Okay, so the thickness is equal to what? So for this case, the thickness is equal to B. Okay, on the other case that I've drawn, the thickness is equal to 2C. Okay, so because from here to here, this dimension is equal to what? 2C. Right? So what you can see down here is how we're going to relate the thickness. Okay, so the thickness orientation is perpendicular to the applied shear force. Okay, so if you look at Vy over here, right? Vy is in this orientation, so it is what? Perpendicular. If we look at Vx over here, sorry, Vz, the perpendicular is what? Is your 2C. Okay, so this is how we are going to determine what is our thickness, right? Remember, I told you the thickness is dependent on our what? The thickness is dependent on where we are interested in. Yes. Okay, so the next thing that we're going to look at, okay, I know there's a lot of rules over here, okay, so are these rules that later on when you apply, it does not seem so bad, okay, later on when we apply, it does not seem so bad, okay. So now, the next one that I'm going to highlight now is, let's see, should I talk to you about first moment of area yet? Sorry, second, okay. Then we're going to look at second moment of area. Okay, we're going to look at second. So we have sort of the what? We have defined what is V. I've talked to you about Q. I've spoken to you about T. Now I'm going to talk to you about I. Okay, so I know some of you do know what second moment of area. Okay, but I'm going to assume that no one know about it. 2c is equal to the height. Jerome, 2c is equal to height. What are you concerned about? Can you speak to me or no? 2c is the thickness, it's not height. Okay, depending on the orientation of your VZ. Okay, or on your applied force. Okay. Oh, 2c is equal to h. Yeah, you're right. You're right. Okay. Yeah, you're right. So 1c over here, 2c equal to here, hc is half is equal to h. You're right. Now, the next thing we are going to look at second moment of area. Okay, second moment of area. And again, I'm going to follow based on what we highlight before, right? So what we highlight before. So I'm going to split this into two so that you will know what are the difference when you study later on. So FF. Okay, I'm going to split this into two. Okay, so the difference is the orientation of the Vy, right? So this is V for Vy, this is for Vz. I'm going to write down here, okay? So analysis for Vy, and then the other side is analysis for Vz, okay? So I'm going to write the second moment of area, okay, is what we call I, okay? And the second moment of area is basically a parameter to determine the resistance of bending. The higher the I value means the higher resistance the bending is, okay? So for this case, right, for this case, like what we've seen over here, for this case, so I'm going to still draw the same cube or the same cross-sectional area, right? Transformation are all the same. So we are looking at now, this is your Vy, okay? And the I we're going to use will be for I what? ZZ, okay? So the orientation of the second moment of area axis of the second moment of area I is perpendicular to the applied shear force. Okay, so this will be IZZ is equal to width multiplied by depth cube divided by what? 12. Okay, so which is the width. Okay, so the width is always, right, the width is always perpendicular to the applied force. Okay, so this is the width. So the width is perpendicular to the applied force, right? And the depth, so this is the depth, right? So this is the depth. Is parallel to the applied force. You can see from here, right? Right. So for this case, this we know that this is equal to B, right? The distance from here to here is equal to 2C based on the diagram. So this is B and this is 2C. So over here, IZZ will be equal. So the width is what? The width is B. The depth is 2C to the cube divided by 12. So this will be equal to 8B C cube divided by 12. So this will be equal to 2/3 BC cube. Okay, that's equal to 2/3 BC cube. Now, if you look at the other side now, if you look at this orientation now, okay, so what we're going to do is the same. Now the applied force is what? Is in the horizontal orientation. Okay, so transformation is still the same, right? Still the same. So what we have now, this is where our Vy is, right? So the axis that we have to consider now, right, is a perpendicular axis intersecting the Vz. Sorry, this is not Vy. I do apologize. So this is your Vz. Okay, so this is your y axis, right? So you consider the perpendicular axis. You don't consider what? You don't consider zz. Vz will have to consider Iyy. Okay, so this will be equal to Iyy. Now this distance over here, right, is perpendicular to the applied force Vz. So this is going to be your width, right? And then over here, this is going to be your what? Be your depth. Parallel to the applied force is your depth. Perpendicular to the applied force is your width. Okay, so we know that the depth over here is equal to B. The width over here is equal to 2C. So the formula is still the same, is equal to width multiplied by depth, power of 3 divided by 12. So now this changes. So the width now is 2C. The depth now is B cube divided by what? 12. So this will be equal to 2B cube C over 12 is equal to B cube C over 6. Okay, so not the same, right? So you can see how the applied force, how the applied shear force will affect your what? Will affect your formula. Okay, you can see over here. Then I'm going to write out the general formula. Okay, so if we're going to see over here now. Now, this takes a bit of thinking. Okay, it's not so easy. So if you look at the orientation over here, right, the shear force is acting in this orientation. Yes or no? That is how the shear force is orientating. So if you look at transformation, this is the shear. So this plane over here will intersect the x-axis. The force applied or the shear stress applied is the y-axis. So if you write down here, so this is shear xy is equal to the shear yx. And based on Vy, right? So if this is Vy, And then Vy will have to divide by what? Will have to be divided by IZZ, right? And the Q will be in QZ, and then we have to divide by our what? Thickness. Okay. So this, if you look at this, the trend is Vy divided